Okay, in this video, we are going to look at the union and intersection operation on Fs. So you might have already studied the union and intersection operations in your discrete mathematics. So the union operation actually refers to the OR operation, the OR clause in set theory. Similarly, the intersection operation actually refers to the AND operation. So we have studied this in digital system design. You might have studied it in discrete mathematics. So the mathematics behind is that union operation refers to the OR and the intersection refers to the AND operation. This is also valid for set theory. So now let's look into how this becomes applicable for FAs. So while designing some FAs, we might have encountered questions having the OR clause or the questions having the AND clause. So there are some standard procedures using which we can easily design for such questions. Let's look into it. Now let us look at this question. This question says that design a DFA to accept binary strings with even number of ones, and even number of zeros. So there are two languages here. You can actually classify this into two different languages. That is binary strings with even number of ones, and binary strings with even number of zeros. So let's say I'm calling this as language 1, L1, and this as language 2. So language 1 is nothing but the binary strings with even number of ones. So let me write it here with even number of ones. And language 2 is strings with even number of zeros. So what we want is not we don't want to find the individual DFAs. We want to design a DFA that will accept the binary strings with even number of ones and even number of zeros. So we wanted to find an intersection. So our language is going to be, our original language is going to be an intersection of L1 and L2. So L1 intersection L2 will provide us L. So we want to design for this language. So what we can do is we can actually do the design for L1 separately and then for L2. And then there are some standard procedures for converting that DFA into the language that is required for L. So let's look into it. So now let us design for L1. L1 is the language which accepts, which is a binary string with even number of ones. So let's design the DFA for L1 first, and then we will design for L2, and then we will combine them. So let's design the DFA for L1. So that is going to be the binary strings with even number of ones. So let me start in Q0. So Q0 is going to be the starting state. Now we know that even number can be 0, 2, 4, 6, etc. So 0 is also a valid even number. So Q0 by itself is going to be a final state, because if you find no ones, then that's also possible. So if you are finding 0 ones, then that's also accepted. So Q0 becomes our final state. Now from Q0, so at Q0, if you are seeing a 0, so if you are seeing a 0, you are going to stay here because you have not seen any ones. So as long as you see zeros. So when you see the 1, you are making a move to Q1, and Q1 is not going to be your final state. So from there, if you see another, so from here, if you see a 0, again you are going to be staying there in Q1 itself. Now, if you see a 1 from Q1, you'll get back to Q0, which is a final state. So now we can verify that so strings like say 1 0 1 0, this contains 2 ones. So what will happen? Let's check it. So upon getting the first one, you'll be shifting from Q0 to Q1, and then you have a 0. You will be at Q1 itself, and then upon getting the next one, you'll be at the final state, and from there you're having one more 0, so you'll be in Q0 itself. So this is the DFA to accept binary strings with even number of ones. Similarly, we can draw the DFA which will accept even number of zeros. It's very easy. You can, instead of, you can actually switch the transitions on 0 and 1. Means you can actually switch the values of 0 and 1 to get that. So let me draw it here. So that's going to be like this, Q0. The only thing is that you're going to switch zeros and ones. So Q0 is going to be a final state. So until you're getting a 1, you're going to stay here. If you're getting a 0, you're going to make a move. And if you're getting a 1, you're going to stay here. And then if you're getting a 0, you're going to come back here. So these are the two Dfas. So this is for L1 and this is for L2. Now we want to design for L1 intersection L2. So we want to actually find L1 intersection L2. So the first step that we need to do is to find the Cartesian product of the states in L1 and L2. So we know that the states in L1 are Q0 and Q1. So let me represent in a set form. So I have Q0 and Q1 in L1, and L2 I have. So anyway, I have to do a different numbering here. Because to avoid confusion, I will do a different numbering here, because Q0 and Q1 is already used here. So let me use Q2 and Q3 here. So instead of Q0 and Q1, I will be using let me erase this. Let me take my eraser and erase this one. So I will be using, instead of Q0 and Q1, I am going to use Q2 and Q3. So my L2 consists of Q2 and Q3. So now I want to find the Cartesian product of the states in the states in L1 and L2. So this is not L1. This is the states in L1. I should write states in L1. Similarly, states in L2. States in L2. So this is the first step that you need to do. So the first step is that you need to do is to take the Cartesian product of the states in L1 and states in L2. Let me write it here. So the first step is that take the Cartesian product of states in L1 and L2. So the Cartesian product will be something like this. It will be all the combinations of values in L1, states in L1 and L2, and that will be Q0, Q2. That will be the first one. The second one will be Q0, Q3, Q0, Q3. Then we have Q1, Q2. Then we have Q1, Q3. Let me write it. Q1, Q3. So this is going to be the Cartesian product of the states in L1 and L2. So that's going to be our first step. Now we know that the final state in L1 and L2, the final state in L1 is Q0, and the final state in L2 is Q2. So we are actually going to design this DFA using these Cartesian products. We are actually going to consider each of them as a single state. We are going to consider each of these states as a single state, and then we are going to redesign our DFA. And remember, Q0 is the final state in L1 and Q2 is the final state in L2. So since we have an AND closure here, we are going to consider the combination which has got both Q0 and Q2 as the final state in our new DFA. So this particular combination, Q0, Q2, is going to be our final state in the new DFA that we are designing. And we are actually considering all these as single states. So now the DFA that we are going to develop will contain also, I think I have missed one. There are only 4 states. Yeah, Q0,
Yeah, there are only 4 states in this example. Okay, so our DFA, our new DFA will contain all these 4 states. Before, if some reduction is possible, we'll do that also. But as of now, our new DFA will contain all these 4 states, and we are also able to identify our final state from this set of states by looking at what is the final state in L1 and what is the final state of the DFA for L2, and then the combination of that will be the final state for the new DFA. Final state for the new DFA. So this is very important. So in this particular method, where we want actually to find the AND closure. So we are interested in finding L1 intersection L2. The final state is going to be the combination of the final states of L1 and L2. That's the first step. Now we'll look at the second step. Now the second step is to draw the DFA, draw the new DFA. So for making, for helping us to draw the new DFA, let's actually draw the transition diagram to make things easier. So we can actually use by using the transition diagram. So let me draw the transition diagram to make the things very clear. So let me say this is going to be my transition diagram. Let me draw it here. So the transition diagram will contain the set of states, and so I have in the new DFA I will be having Q0, Q2. That's my state. I have Q0, Q3. I have Q1, Q2. I have Q1, Q3. So these are the new states which I am having. Now I have to design for 0 transition and for 1 transition. So this is my 0 transition, and this is my transition on 1. Okay, so let me write the transitions here. Now we are interested in knowing the transition of Q0, Q2 upon getting a 0. So let's try to understand how it can be done. So we want to know the transition from Q0, Q2 upon getting a 0 first. So we know that from this transition diagram of L1, by looking at the transition diagram of L1, we can understand that Q0 on transition 0 will get back to Q0 itself. So Q0 on 0 is Q0 itself. Okay. And what about Q2 on getting a 0? So if you look at the second transition diagram, we can understand that Q2's transition on 0 is going to Q3. So we can write that here. Okay, so the transition of the state Q0, Q2 on 0 is going to be Q0, Q3. So I can write this as Q0, Q3. Similarly, for the transition on 1, that is, I want to know the transition of Q0, Q2 upon getting a 1. So I should look at Q0 upon getting a 1 in L1, it goes to Q1. So Q1, and what about Q2? Q2 upon getting a 1 stays at Q2. So it is going to be Q2. So I will have to write the transition of Q0, Q2 upon getting a 1 is Q1, Q2. Q1, Q2. Similarly, we have to fill for all other states. Let me do one more. So we'll look at Q0, Q3. So Q0, Q3. If you look at Q0, Q3, upon getting a 0 from Q0, Q3, we know that Q0 upon getting a 0 is Q0 itself. From Q3, if you are getting a 0, you're going back to Q2. So it is going to be Q2. Similarly, Q0, Q3 on 1. Let's check that. Q0 on 1 goes to Q1, and Q3 on 1 goes to Q3 itself. Okay, so Q0, Q3 on 0 goes to Q0, Q2. Let me write it here. This is going to be Q0, Q2, and Q0, Q3 on 1 has Q1, Q3. So here it is going to be Q1, Q3. Similarly, let me fill all other fields. Now, based on this transition diagram, it becomes very easy for us to design the DFA. So let's start designing the DFA. So we already know that Q0, Q2 is going to be our starting state as well as final state. So I will double circle it and also provide an arrow from the left side indicating that that's the starting state. And let me write all other states in which are here. So that is I have Q0, Q2, I have Q0, Q3. Then I have Q1, Q2. Then I have Q1, Q3. So let's now draw the transitions. We know that the transition on Q0, Q2 upon 0 is Q0, Q3. So upon 0 we have Q0, Q3, and upon 1, Q0, Q2 upon 1 is Q1, Q2. So there is an arrow like this. And now we have to write the transitions from Q0, Q3. From Q0, Q3, upon getting a 0, it goes to Q0, Q2. Upon getting a 1 from Q0, Q3, it goes to Q1, Q3. So this is the transition. And from Q1, Q3, and from Q1, Q2, let's complete Q1, Q2 first. And from Q1, Q2, when I get a 0, I go to Q1, Q3. So when I get a 0, I go to Q1, Q3. And from Q1, Q2, if I get a 1, I go to Q0, Q2. So that's going to be here. The DFA looks very interesting. And we have to draw the transitions from Q1, Q3 as well. From Q1, Q3, if I'm getting a 0, I'll be going to Q1, Q2. So that this transition. And also from Q1, Q3, if I'm getting a 1, I will go to Q0, Q3. Upon getting a 1, I'll be going to Q0, Q3. Okay. So I think everything is fitting in. The transitions, all transitions are present from all other states. Okay. Now this is our DFA. This is our DFA representing, this is the design of the DFA which will accept binary strings with even number of ones and even number of zeros. So this becomes very easy. So if you know the procedure for doing the intersection, that's basically an AND operation. So the procedure is very easy. That is the first thing that you need to do is take the Cartesian product of the states in L1 and L2, and then draw the new DFA by using the transition diagram. Also, you have to identify the starting state and final state. And the starting state and final state will be the combination of the starting states and final states in L1 and L2. Now, to provide more clarity, I have added it as a third step here, just to provide more clarity on that. So the state containing both the final states, it's very important, both the final states in L1 and L2 is chosen as the final state in the new DFA. Similarly, this is also applicable for the starting state. So the state containing the starting states in L1 and L2 is chosen as the starting state of this starting state of the new DFA. So that's how we identify this. And now the OR clause is very easy. So if the question is like design a DFA to accept binary strings with even number of ones, and instead of and, if I have an OR clause there, look at the question. I'm modifying the question. Design a DFA to accept the binary strings with even number of ones, or instead of and, I'm saying or, even number of zeros. Now the only difference that you need to do is in the third step. So the only difference that you need to do is in the third step. So in the third step, instead of marking the state containing both the final states in L1 and L2, I'm going to modify it slightly. Instead of both, I will say any one of any one of the final states in L1 and L2. So instead of saying, in the case of an intersection or in the case of an AND operation, we have chosen the final state as the state containing both the final states in L1 and L2. But here, what I'm going to do is I'm going to modify it slightly. I will choose the state containing any one of the final states in L1 and L2 is chosen as the final state. So there can be multiple final states as well. So it can be modified as states. Okay, so the state containing any one of the final state in L1 and L2 is chosen as the final states. So let's modify this. So Q0, Q2. So which are all the final states in the new DFA? So Q0, Q2 contains one of the final states. In fact, it contains both the final states. That's Q0 and Q2. Here, Q0 and Q3 also now becomes a final states. It's very important to note that Q0, Q3 also becomes a final state because Q0 is a final state in L1. Similarly, Q1, Q2 also becomes a final state because that contains Q2. Q2 is the final state in L2. Now Q1, Q3 will remain to be a non-final state because it doesn't contain any final states at all. So this is very important to note that if the question is based on an OR clause, so the question is asked for OR, the only modification that you need to do is in the third step. What you need to do is you have to select those states containing any one of the final states in L1 and L2 are to be chosen as the final states. That's the only modification that you need to do. For starting state, it remains the same. So the combination of states of L1 and L2, the starting state, the combination of starting state in L1 and L2 is going to be the starting state in the new DFA. So there is no change for the starting state. The only change is reflected in the case of final states. I think I should make a slight modification here because I said both the final states. In this particular example, it is valid, but for some other examples, there can be multiple final states in L1. Also, there can be multiple final states in L2. So I should say it as all final states for the first definition. So let me for providing more clarity, let me change this as the state containing all the final states in L1 and L2 is chosen as the final state. Similarly, so when you have the other one, that's for the OR operation. For the OR operation, instead of all, the state containing all, instead of saying all, you can say any one of the final states in L1 and L2 is chosen as the final state. Final states, I should say, there can be multiple final states. So I should say state or states. Okay. Now let's recap what we did. We actually started with designing the machine for L1 and L2. And then we said we could design the AND operation on L1 and L2. We designed the machine for L1 intersection L2. That is the AND operation. We have also designed the union of L1 and L2. That is L1 union L2. That is nothing but the OR operation. Remember, this is called as intersection. This is called as intersection. And this is called as union. Now, in this example, we had two states in L1. L1 had two states. Similarly, L2 also had two states. So the Cartesian product of L1 and L2 will contain 2 into 2. That's 4 states. And that's why this was very easy. The new DFA contains only 4 states. So remember, this method can be made practical only if the number of states in L1 and L2 is going to be less than or equal to 3. So if L1 contains 4 states instead of 2 states, if L1 contains 4 states, and L2 also contains 4 states, let's say. And then the Cartesian product will contain 16 different states. And 16 different states, it is going to be difficult to manage because there will be 16 entries in your transition table. So you have to find the transitions for all the 16 entries and then draw a transition. You have to draw a DFA containing 16 different states. So if there is no reduction possible, then you have to draw your transition table containing 16 different states. And that's going to be difficult. So this method is practical only if the number of states is less than or equal to 3 in L1 and L2. Now this question was about to design a DFA to accept binary strings with even number of ones and even number of zeros. So this question can be asked in many different ways. So this question actually wanted us to find even number of ones and even number of zeros. So there can be different ways of asking this question. So it can be like even number of ones and odd number of zeros, or odd number of zeros and even number of zeros, odd number of ones and even number of zeros. Similarly, odd number of ones and odd number of zeros. So this question can be framed in many different ways, right? So this could be also asked for or clause or the and clause. So there can be 8 different questions framed out of this question. So you should be familiar to solve all this. For this kind of a question, you can actually apply this union and intersection operation and then solve that. So some questions are provided in the assignment section, which you have to solve and submit. So let's look at the assignment section. So before moving to the assignment section, let's look at a question very quickly. So the question is, give a DFA for the following language over the alphabet 01. That means it's a binary string. So the language is defined like this. Language is all the words such that the words start with 1, and has odd length, or starts with 0 and has an even length. So since this OR clause is here, we will be tempted to use the method that we were discussing. But let's quickly design the DFAs for L1. So I can actually say that this is going to be language 1 and this is going to be language 2, and then start designing it. So let's look into it and check whether it is possible. I also remember that this question is asked in your university question, May 2019, for just 4 marks. So looking at the marks itself, you should identify that we should not follow the method that we were discussing, and you should try to solve it trivially. So I will show you the problem if you use the method which we were telling about. So let's start designing for L1. So for L1, the string should start with 1 and should have an odd length. So I start at Q0, and then upon getting a 1, I will move to Q1, and then it has an odd length. It should have an odd length. So if you get a 0, 1 anything, you may move to Q2, and that should not be an accepting state. That should not be an accepting state because whatever ends up in Q2 will be even. Okay, now from Q2, if you are getting one more string, you can actually move back to Q1, and now Q1 becomes your final state. And remember that there has to be a dead state here. So if you're getting the starting alphabet, the starting symbol as a 0, then it should never be accepted. So it should be going to a dead state. Let's call the dead state as Q3. Okay, so I think our the DFA for L1 is ready. So you can see that L1 itself has got 4 states. It has got 4 states here. 4 states, that is L1 itself is having 4 states, that is Q0, Q1, Q2, and Q3. So let's check for L2. So L2, it is given that it should start with a 0. It should start with a 0. So let's start numbering it from Q4 onwards. So starting state. So it should start with 0, and then it should have even number of even length. So it should not accept 1, 3, or 5, something like that. It should always accept only even combinations. So so what I can do here is that I should have a final state here, that is Q6. So any movement, any symbol after I found a 0, I will make a move to Q6, and Q6 is marked as a final state. Right. Now, if I see a 1 as the initial alphabet, initial symbol, then I will be moving to a dead state, that is Q7. Okay. So can we minimize it further? Any possibility to minimize this further? Now, is it possible to avoid Q6 and then say I will move from Q5 to Q4 upon seeing a 0 or a 1? So I will cut this portion, and then I'm saying I will upon seeing a 0, 1, I will move to Q4 and I mark Q4 as a final state. Is it possible? So you have to carefully look at the question. It says that it should start with a 0 and has an even length. So even though 0 is an even number, 0 is an even length, but it is said that it should start with a symbol 0. So the minimum size of the string should be 2. So this would have been correct if the starting with 0 condition is not mentioned. So so this cannot be applied here. So okay, I think I forgot to mention one of the transitions. That is from Q6, I should mention the transition back to Q5 upon seeing a 0 or a 1. This should also be present, right? Still L2 has got 4 states. So the total number of states in the Cartesian product will be 16. So if there are 16 different states, in the Cartesian product, we will have 16 different states in the states when we design the union of L1 and L2, and that becomes very difficult. So if the number of states is more than 3, then it becomes difficult to actually follow the intersection and union method that we have discussed. So it is very important that you should look carefully at the question and then try to solve it trivially if that is possible. This particular question can be solved trivially in a very easy way. So let's try to do that. So let's say the starting state is Q0, and from Q0, if you see the first symbol as a 1, okay, if you see the first symbol as a 1, then the language is such that if the word start with a 1, it should have an odd length to be accepted. So let's try to accept only odd length strings after seeing a 1. So when you have seen a symbol of 1 from Q0, then you'll reach Q1. And remember, Q1 has to be an accepting state because you have seen one symbol and 1 is an odd number. And if you see anything more than that, if you're seeing one more symbol, then that's an even number, and that should not be accepted. And this should not be accepted, right? So from there, from Q2, if you see one more symbol, you can actually move back to Q1, because again, that becomes an odd number. And this part of our DFA will accept words starting with 1 and has an odd length. Similarly, if you see 0 as a first symbol, then we should accept all the words having even length. So when you see a 0, you are at, say, Q3. You are at Q3, and from Q3, if you see one more symbol, that means you have seen 2 symbols, and 2 is an even number and it should be accepted. So Q4 becomes a final state here. And from Q4, if you see one more symbol, you can actually go back to Q3. and it is a non-final state, because from Q4, if you see one more symbol, that means you are looking at odd number word. And from Q3, if you again see one more symbol, you will be coming to Q4, which is a final state. And this happens because you have seen even number of symbols. So this is the DFA for our language, and this is not very difficult. This is very easy to be designed trivially. So you have to look at the question carefully, and if it's a very simple question involving many states like this, then you should always look for the trivial methods. So I just wanted to emphasize this, just because you may be tempted. So looking at the question, you should not get tempted to use union and intersection procedures always. It might be a very easy question to be solved directly. So the assignments are to design a DFA to accept binary strings with even number of ones and odd number of zeros. The question that we attended was even number of ones and even number of zeros. Here it is slightly different. You have to figure out DFA to accept even number of ones and odd number of zeros. So the exact same question with OR clause is asked here. So once you design this becomes very easy. The only thing that you need to do is convert the states containing any one of the final state as a final state. So here again, one more question is the vice versa, odd number of ones and even number of zeros. Similarly, the or operation of that. Even though there are 4 questions, if you find the answer to one of them, the second one becomes very trivial. Similarly, if you find the answer to third one, the fourth one becomes very trivial. So you can work out this as an assignment and submit it in the next week.